Imagine a magic box. You drop something in, and something else comes out. That's a function. It's a rule, a machine, that takes an input and gives you back exactly one output. Think of a vending machine. You press button A4, and you get a specific packet of chips. You don't press A4 and sometimes get chips and sometimes get a chocolate bar. That one-to-one rule is the heart of the idea. A function is a consistent, predictable relationship where each input is paired with one, and only one, output. Why do we care about this machine? Because the universe is full of cause and effect. You study for a certain number of hours, you get a certain test score. You push the accelerator pedal a certain amount, your car goes a certain speed. A function lets us capture that relationship, put it in a box, and use it to predict what will happen. If I know the function, I can tell you the output for any input. This is the absolute bedrock of calculus. In calculus, we don't just ask what is the output, we ask how fast is the output changing when I change the input. But you can't even ask that question until you first have a function. Let's open the box. We give the function a name, usually a letter like f. The input is often called x. So we write f of x, which looks like f(x), to mean the output when the input is x. The set of all inputs you are allowed to drop in is called the domain. For a vending machine, the domain is the set of all working buttons. The set of all outputs that can possibly come out is called the range. For the machine, that's all the snacks it holds. The most important rule is the one output rule. For every single input in the domain, there is one, and only one, output. If a rule gives you two possible outputs for the same input, it's not a function. For example, if I ask you to name your siblings, one person might have two siblings, so you as an input gives multiple outputs. That relationship is not a function. Let's solve a real problem. Imagine an auto rickshaw ride. The fare is 25 rupees to start the meter, plus 15 rupees for every kilometer you travel. Is this a function? Let's check. The input is the distance traveled in kilometers. The output is the total fare in rupees. For any distance, say 5 kilometers, there is only one possible fare. The rule is, fare equals 25 plus 15 times the distance. If we call the distance d, we can write this function as f of d equals 25 plus 15d. So, what's the fare for a 5-kilometer ride? We plug in 5 for d. That's 25 plus 15 times 5. 15 times 5 is 75. 25 plus 75 is 100 rupees. There's no other answer. It's a perfect function. This same method, finding a rule and checking for a single output, works for calculating the area of a square from its side, or the distance a car travels at a steady speed. A graph is simply a picture of a function. You already know a function is a rule that takes an input and gives exactly one output. To draw that rule, we make a dot for every input-output pair. The horizontal position of the dot is the input, x, and the vertical position is the output, f of x. So the point is always x, f of x. When you plot enough of these points, they join up to form a line or a curve. That curve is the graph of the function. It shows the whole rule at a glance, like a map of where every input lands. Why turn a function into a picture? Because our eyes are brilliant at spotting patterns. A list of numbers like 1 maps to 1, 2 maps to 4, 3 maps to 9 is hard to scan. But the graph of x squared is a smooth U-shape. You see instantly that outputs grow faster as x gets bigger, and that the function is symmetric. Most importantly, a graph lets you check the most fundamental rule of a function: one input gives exactly one output. You can see this rule visually, without calculating anything. If a graph ever doubles back on itself vertically, it means one input is trying to give two different outputs, and that breaks the rule. The graph is your lie detector for functions. Here is the vertical line test. Imagine drawing a vertical line, a line straight up and down, anywhere on the graph. This line represents a single input value, a single x. Now count how many times that vertical line hits the graph. If it hits exactly once, then that input has exactly one output. Good. If it hits more than once, then that single x is paired with multiple y values. That breaks the one output per input rule, so the graph cannot be a function. If the line misses the graph completely, that just means that x is not in the domain, which is fine. The test is simple: any vertical line must cross the graph at most once. Let's test it. A parabola, like y equals x squared, passes, any vertical line hits it only once. But a circle fails, a vertical line through the middle hits the top and the bottom, giving two outputs for one input. Let's use the vertical line test on a real example. Suppose you see a graph that looks like a perfect circle centered at 0 with radius 1. You might wonder, is this circle the graph of a function? To find out, we pick an input. Let's choose x equals 0, right at the center. Imagine drawing a vertical line through x equals 0. That line goes straight up the y-axis. It hits the circle at 2 points, at y equals 1, the top of the circle, and at y equals -1, the bottom. That means the input 0 is trying to give two different outputs, 1 and -1. A function must give only one output for each input. So the circle fails the vertical line test. It is not a function. But notice, if we only took the top half of the circle, that would pass, every vertical line hits it just once. We've seen that a function is like a machine that takes an input x and gives back an output f of x. Now let's meet the simplest machines of all. The constant function just ignores the input and always returns the same number c. Think of a vending machine that always gives you the same candy bar no matter which button you press. The identity function is even simpler, it gives you back exactly what you put in. If you put in 3, you get 3. If you put in 10, you get 10. It's the do-nothing machine. A linear function is a slight twist on the identity, it multiplies the input by a number m and then adds another number b. So it scales and shifts the input. These three are the very first building blocks of a huge family called polynomials. Why do we care about these simple machines? Because they let us model the world. A constant function models something that never changes, like the speed of light in a vacuum. A linear function models a steady rate of change. Think of a car moving at a constant speed, where distance equals speed times time. But the real magic is that we can combine these simple pieces, adding, multiplying, and scaling them, to build curves that can model almost anything: the arc of a basketball, the growth of a population, the shape of a roller coaster. And here's the crucial part for calculus: these polynomial graphs are smooth and unbroken. They have no gaps, no sharp corners, no sudden jumps. That smoothness is exactly what we need to study rates of change and areas under curves, which is what calculus is all about. Let's see how these functions work on a graph. For a linear function f of x equals mx plus b, the number m is called the slope. It tells you how steep the line is. If m is 2, for every step you take to the right, the line goes up by 2. If m is negative, the line goes downhill. The number b is the y-intercept. It tells you where the line crosses the vertical y-axis. That's your starting point when x is 0. Now, if we multiply the input by itself, we get f of x equals x squared, a quadratic. Its graph is a beautiful U-shaped curve called a parabola. If we cube the input, f of x equals x cubed, we get an S-shaped curve that swoops down and then up. A polynomial is just a sum of these kinds of terms, like x squared, x cubed, or just a number, each multiplied by a coefficient. Let's use a linear relationship to solve a real problem. Imagine you want to find the height of a tall tree without climbing it. You can use a simple trick with a right triangle. Stand 10 meters away from the tree and look up at the top. Suppose the angle your line of sight makes with the ground is exactly 45 degrees. At 45 degrees, something special happens. The height of the tree and your distance from it form two equal sides of a right triangle. It's like half a square cut diagonally. So the tree's height above your eye level is exactly the same as your distance on the ground, 10 meters. If your eyes are 1.5 meters above the ground, the total tree height is 10 plus 1.5, which is 11.5 meters. The relationship here is linear, height equals 1 times distance. This idea of using a steady ratio, a slope, to find an unknown is at the heart of linear functions and trigonometry. A rational function is simply one polynomial divided by another, like a fraction. Think of f of x equals 1 over x. Here, the numerator is the constant polynomial 1, and the denominator is the identity function x. The big new idea is that the denominator can become 0. For f of x equals 1 over x, when x is 0, we'd have 1 divided by 0, which is undefined. So the function simply doesn't exist there. On a graph, this shows up as a sudden break. The curve is torn into separate pieces, unlike the smooth, unbroken graphs of polynomials you've seen before. Why do we care about these broken graphs? Because they model real situations with hard limits. Imagine a car's engine. As you push it faster, the speed increases, but it can never reach an infinite speed. There's a physical limit. A rational function captures this idea mathematically. The forbidden x value, where the denominator is 0, acts like an unbreakable wall. By studying how the function behaves right next to that wall, shooting up to infinity or down to negative infinity, we learn about extreme behavior, which is the heart of calculus. It's our first tool for understanding the infinite. So how does this work? A vertical asymptote is a vertical line, like x equals 0 for 1 over x, where the function is undefined because the denominator is 0. As x gets closer and closer to 0 from the right, the fraction 1 over a tiny positive number becomes a huge positive number, so the graph shoots up. From the left, 1 over a tiny negative number becomes a huge negative number, so it shoots down. A horizontal asymptote is different. It's about what happens when x gets very large, heading to positive or negative infinity. For 1 over x, 1 divided by a giant number is nearly 0, so the graph levels off along the line y equals 0. In general, we compare the degrees of the numerator and denominator polynomials. If the denominator's degree is larger, the horizontal asymptote is y equals 0. If they're equal, it's the ratio of the leading coefficients. Let's solve a concrete problem. Suppose you're printing custom t-shirts. There's a fixed setup cost of $100, and each shirt costs $5 to print. The total cost for X shirts is $100 plus $5X. The average cost per shirt, which we'll call C of X, is the total cost divided by the number of shirts. That's the rational function C of X equals 100 plus 5X, all over X. What's the average cost if you print 1,000 shirts? We plug in X equals 1,000. That gives 100 plus 5,000, all over 1,000, which is 5,100 divided by 1,000. That works out to $5.10 per shirt. Notice that as X gets huge, the 100 fixed cost becomes negligible, and the average cost approaches $5. That's the horizontal asymptote y equals 5. Imagine you have a magic bank account that doubles your money every year. You start with 1 rupee. After 1 year, you have 2 rupees. After 2 years, 4 rupees. After 3 years, 8 rupees. This is repeated multiplication, multiplying by 2 again and again. An exponential function captures this idea. It's written as f of x equals a to the power x, where a is a positive number not equal to 1. The input x is the number of times you multiply. The output grows incredibly fast, that's why we call it explosive growth. And you can put any real number into it, even fractions or negatives, so its domain is all real numbers. Why do we care about this? Because the world is full of things that grow by multiplying, not by adding. Bacteria in a petri dish double every hour. Money in a compound interest account grows by a percentage each year. Even the cooling of a hot cup of tea follows an exponential decay. If we only had the exponential function, we could ask, after 3 hours, how many bacteria are there? That's easy, just plug in x equals 3. But the really useful question is the reverse, how long until the bacteria count reaches 1 million? To answer that, we need to run the exponential backwards. We need its inverse. That inverse is the logarithm. So, how does this inverse actually work? The logarithm is the function that undoes the exponential. If a to the power x equals y, then the logarithm base of y is x. It asks, what power do I raise a to get y? The word logarithm comes from Greek words meaning ratio number. It was originally used to simplify calculations with ratios. Now, here's the beautiful visual. Take the graph of an exponential function, like 2 to the x. If you reflect that graph across the diagonal line y equals x, you get the graph of the logarithm. Every point x, y on the exponential becomes y, x on the log. This reflection instantly shows you why the logarithm's domain is only positive numbers, because the exponential's range, its outputs, are only positive. You can't take the log of 0 or a negative number, just like you can't get 0 or a negative number from a positive base raised to any real power. Let's solve a concrete problem. A lab dish starts with 100 bacteria. They double every hour. The growth function is number of bacteria equals 100 times 2 to the power t, where t is in hours. We want to know, after how many hours do we have 1 million bacteria? We set up the equation, 100 times 2 to the t equals 1 million. First, divide both sides by 100 to isolate the exponential. 2 to the t equals 10,000. Now we need the inverse. The logarithm base 2 undoes the 2 to the power. So t equals log base 2 of 10,000. We can compute this. 2 to the 10 is 1024, and 2 to the 14 is 16,384. So 10,000 is between them. Using a calculator, log base 2 of 10,000 is about 13.29. So it takes about 13.3 hours to reach 1 million bacteria. Imagine a point moving around a circle of radius 1, centered at the origin. As it travels, we track 2 things, how high it is and how far across it is. The height, which is the y-coordinate, is called the sine of the angle. The horizontal distance, the x-coordinate, is called the cosine. The angle is measured from the positive x-axis, going counterclockwise. So sine and cosine are just the coordinates of a spinning point. They are functions because for every angle, there is exactly one height and one width. Why do we care about a spinning point? Because so many things in nature go back and forth or round and round. A swing, a guitar string, the alternating current in your house, even the seasons, they all repeat. Sine and cosine give us a language to describe that repeating up-down motion precisely. If you know the angle, you know exactly how high or how far something is. For example, if you're on a Ferris wheel, your height above the ground follows a sine wave. These functions turn circular motion into a smooth, predictable wave. Let's build it from the circle. We start with a circle of radius 1. Pick an angle and draw a line from the center to the edge. That line is the radius, and its length is 1. Now drop a vertical line down to the x-axis. You've made a right triangle. The radius is the hypotenuse. The vertical side is the height, that's sine. The horizontal side is the width, that's cosine. Because the hypotenuse is 1, sine is just the opposite side, and cosine is the adjacent side. The word sine comes from an old word for a bowstring or fold, and cosine means the sine of the complementary angle. Tangent is the slope of the radius, sine divided by cosine. It tells you how steep the line is. Let's solve a real problem. You want to know how tall a tree is, but you can't climb it. You stand 20 meters away and measure the angle from the ground to the top. It's 30 degrees. The tree height is the opposite side, and your distance is the adjacent side. So we use tangent, which is opposite over adjacent. Tangent of 30 degrees is height divided by 20. We know from the special triangle that tan 30 degrees is 1 over root 3, about 0.57. Multiply both sides by 20, height equals 20 times 0.57, which is about 11.5 meters. The tree is about 11.5 meters tall. This same method works for any tall object, a building, a mountain, even a star if you know the baseline. Imagine a toll road where a car pays one price, a truck pays a higher price, and a motorcycle pays a lower price. The cost depends on which category your vehicle falls into. A piecewise function works exactly the same way. Instead of one single rule for every input, it switches between different rules depending on which piece of the input line you are on. The most famous example is the absolute value function, f of x equals the absolute value of x. For positive inputs, the rule is just give me back the same number. For negative inputs, the rule flips to give me back the opposite, the positive version. So it is literally two different linear rules glued together at 0. Why do we care about these patchwork functions? Because the real world is full of sudden changes. A shipping company doesn't charge you smoothly for every extra gram, the price jumps at whole kilogram thresholds. A tax bracket changes your tax rate when your income crosses a certain line. These situations cannot be captured by a single smooth polynomial or a gentle wave. Mathematically, piecewise functions are our first look at where a graph stops being well-behaved. The absolute value function has a sharp V-shaped corner at 0. A step function has a sudden vertical jump. These are the exact spots where calculus ideas like limits and derivatives get interesting, so we study these functions now to prepare for those big concepts later. So how do we build one of these? We simply write the function as a list of cases. For the absolute value, we say, if the input x is greater than or equal to 0, use the rule f of x equals x. That is the green right-hand piece of the V. If x is less than 0, use the rule f of x equals negative x. That is the orange left-hand piece, which flips the negative sign to make it positive. Notice how the two pieces meet at the origin, creating that sharp corner. A step function is even simpler. For any weight from 0 up to 1 kilogram, the cost is $5. For weight from 1 to 2 kilograms, the cost jumps to $8. Each piece is just a flat constant, and at the threshold, the graph leaps up instantly. Let's solve a concrete problem. A courier company charges $5 for any package weighing up to 1 kilogram. For any weight above 1 kilogram, up to 2 kilograms, they charge a flat $8. Let's write this as a piecewise function, where the input x is the weight in kilograms. The first piece, for x greater than 0 and less than or equal to 1, the cost c of x is 5. The second piece, for x greater than 1 and less than or equal to 2, c of x is 8. If we plot this, we get two flat horizontal segments. At x equals exactly 1, the cost jumps from 5 to 8. There is a gap, a discontinuity. This is a perfect, everyday example of a step function, and it shows exactly the kind of non-smooth behavior that piecewise functions are designed to capture. We already know a function is a rule that takes an input and gives exactly one output. But why learn about so many types? Because the world is full of patterns, and each function type we've studied is a tool to describe a different kind of pattern. A straight line, a smooth curve, a repeating wave, they all follow the same basic function definition, but their shapes and behaviors match different real-life situations. Spotting which function fits a situation is the first step to understanding and predicting it. Each function type solves a specific real-world problem. Polynomials, especially quadratics, give us parabolas, that's the path of a ball you throw, or a fountain's arc. Rational functions, with one thing divided by another, model rates like average speed, distance over time. Exponentials describe things that grow or shrink by a constant factor, like a virus spreading or radioactive material decaying. Logarithms are the inverse, they compress huge ranges, which is why we use them for earthquake magnitudes and sound decibels. And trigonometric functions, born from the circle, perfectly capture anything that repeats in a smooth wave, sound waves, ocean tides, even temperatures over a year. How do we tell them apart? It's all in the formula's structure. A polynomial like x squared has a smooth, bowl-shaped curve. A rational function like 1 over x has a break, an asymptote, where the denominator is 0, so the function can't exist there. An exponential like 2 to the x climbs faster and faster, while its inverse, log base 2 of x, grows slower and slower. And a sine wave just keeps going up and down forever, never settling. The domain tells you what inputs are allowed, and the shape tells you the behavior. Is it shooting to infinity, leveling off, or repeating? Let's make it concrete with a sound wave. A pure musical note, like the A above middle C, vibrates the air 440 times per second. We can model that pressure change over time with a sine function. The input is time, the output is air pressure. The wave's height, its amplitude, is how loud the sound is. The number of cycles per second, the frequency, is the pitch. Right now, we can just draw the wave. But calculus will let us find exactly how fast the pressure is changing at any instant, that's the derivative, and where the pressure hits its maximum and minimum, that's finding the peaks. All these different function types share the same core idea, but calculus gives us the tools to analyze their rates of change, their peaks, and the areas under them, no matter their shape.